Hello and welcome back to my channel. So today's we're going to be, continue to talk about the test statistics for our estimator. So we already know in the previous video that beta hat goes to normal distribution of this one, okay? So technically at this point we can already apply the test statistics based on the normal distribution. But here are some minor issues that we still haven't been solved yet, which is the sigma square. So we know that the sigma square is actually equal to, it's actually the variance of the error term, right? So it's a variance of error term. But remember, like in the very beginning of this series, I mentioned that the error term is some true value for the population, right? And it's something that exists, but in practice, it's hard to find out. So instead of using apply the normal distribution, in regression analysis, there's something that often be used, which is t-distribution, and the expression goes like, for our beta, it goes like these. This goes to sort of t-distribution. And you might ask, hey, wait a minute, where does this strange-looking guys come from? And that's actually going to be what we're going to be discuss for today's video. And okay, let's just break it down a bit by bit. So first of all, I'm just going to give you the definition of our this S beta hat. It's actually the standard dividends for our beta hat. So this S beta hat is going to be equal to sigma hat square divided by this term. So this is actually exactly the same thing. Instead, we replace the sigma square with the estimator of sigma square. So what is the estimator of sigma square? Well, you might be tempted to say that since we don't know what mu is, but what we do know is actually the mu hat, because mu hat is our residual, right? So that's something we can obtain based on our OLS model. Then, but here, instead of divided by n, we actually need to divide it by n minus 2. And this is actually the degree of freedom. Okay, degree of freedom in our systems. And well, I think this is actually deserves, this topic really deserves different videos. But today's, I don't want to waste too much time on that, but I still would like to give you some intuitions, because since we know that our estimator alpha and beta can all be written in a function that in terms that related to our mu hat, right? Let's say it's a mu hat. That's a g of mu hat. Just remember, I'll just write it for real quick, like beta hat equals to beta plus that big things, right, and times mu hat. This is something we learned previously. And in other words, these two functions are kind of like some constraint we have for the system. So let's say, suppose we have 4, the n equals to 4 mu hats 1, mu hats 2, mu hats 3, and mu hats 4. So let's say if we already know either two of them, let's say we know mu1 and mu2, mu hat 1 and mu hat 2. And can we solve for mu hat 3 and mu hat 4? Yes, because we have two functions right here. We have two functions and two unknown variables. Then we can just solve the function, and we will know what the mu hat 3 and mu hat 4 is. So in other words, like the number of the variable that can goes free or can be randomly selected is only like 2 in this system. Let's suppose we only have 4, okay. And the rest of the 2 is going to be kind of like constant, like mu3 and mu2 are viewed as constant, and then it's going to have no effects on the sigma square. So we have to kick them out, right? It's going to be -2. So I hope this can sort of, make some sense. As an analogy, let's say if we are in a multivariable cases and we have different more, like some gamma parameters to estimate, then in that case, this number will also be increased by another one because we're going to have yet another constraint. So actually the number behind the minus sign is actually exactly going to be equal to the number of constraints we have. Okay, and maybe I will just talk more about that in the future. Anyway, so we already know the expression for our sigma hat square. And also you might ask, well, in this expression, like the beta here is also the true value for population, and we don't know beta, right? But actually in the test statistics, we always going to have some null hypothesis. And for the regression model, the null hypothesis gonna, just normally gonna goes like beta equals to 0. And the alternative is going to be beta is not equal to 0. So we kind of assigned the beta with a certain value, and that is something we wanted to verify, okay? So in that case, we will know that this beta hat is based on a model, and this is based on the assumption, and this is some number we can calculate out, and together we can calculate out this t value, okay? But you're probably going to ask me, hold on, like, why this strange-looking guys goes to some t distribution? Well, to understand that, then we need to go back and just look at the definition of the t distribution. So first of all, let's assume there is a variable z, and that is z is equal to y divided by some square root of x divided by m, where this y is going to goes to standard normal, and this x will goes to some chi-square distribution with a degree of freedom m. Okay, so just look at this this form. We already kind of, find some clue, because how do we standardize normal distribution? For example, if we were to standardize this beta, well, we just minus its mean and divided by the square root of its variance, right? So here in our case, this thing as a whole will goes to a standard normal distribution. And this is something already looks very similar to our destination. So the problem then becomes, do we really have some chi-square distribution in our case? Let's say this is our y. Well, we do, because remember, if based on the OLS assumption, the our mu I will goes to some normal distribution. And if we standardize the mu I, then we will have mu I divided by sigma. This, if we okay, I forgot to mention that let's say xi square will goes to chi-square distribution of n if xi goes to each individual xi goes to some normal distribution, okay? So now these things will goes to some standard normal distribution. And if we take square and sum them up, which is these things, okay? And that will goes to a chi-square distribution of freedom of degree n. So, but here again, like, we don't really want to use this mu because we don't know what mu is, but instead, let's try to replace the mu hat. So if we replace the mu hat, the degree of freedom, just in the same manner, it's also going to be decreased by 2, right? So these things will goes to a chi-square distribution with a degree of freedom of n minus 2. So let's define this as our x. So now let's try to plug them in to this expression, see what's going to happen. Okay, so we have z equal to beta hat minus beta divided by this guy. Okay, this is our numerator, and for denominator, we have this guy as our x, and gonna divide it by its degree of freedom. Here is n minus 2, and the whole things will take the square roots, and this gonna become n minus 2. So this thing should go to a t distribution of n minus 2. Okay, so this is already looks very similar. Let's see if we can do some simplification. Well, in actually, like this, let me write this down, like write this whole terms down a little bit. So this is going to be equal to, okay, let me adjust my camera. So this is going to be equal to the sum, 1 over sigma square times the sum of mu I squared divided by n minus 2. And remember, like we defined our estimator of sigma square equal to this term. And this is exactly going to be the same as here. So now this expression just becomes the square root of our sigma hat square divided by sigma square. Okay, cool. And if we further just try to simplify this whole term, we can find out that this annoying sigma square just magically cancel out with each other. Okay, sorry, I sort of made things on the fly a little bit. So here, so if we were trying to simplify this, we just times, for both numerator and denominator, we times the square roots of sigma square over the sigma hat square, so that the denominator is just going to be cancelled out. And for the numerator, we know that the square root of sigma square will just be cancelled with this term. So this annoying sigma square that we don't know just no longer exist in our expression. And finally, what we're going to have, or this is just some very simple algebra, is this expression down here. So this is beta hat minus beta divided by the square root of sigma hat square over this guys. So we know that this term will go to our t distribution with n minus 2. Okay, maybe next video let's do some examples so that you can understand this better. I'll see you in the next one.